about protecting outsourced data against key exposure. This is a work that I did with my supervisor, Mimi, and with Mathieu Rombaud. We are all from Telecom ParisTech. Outsourcing data storage is a widely used, comfortable, cost-effective solution. It is used by mere users like us that want just to store their photos on the cloud, but also by enterprises that cannot or do not want to afford the private cloud infrastructure. But this comfortable solution raises several security challenges. First, a user may simply not trust the storage providers. Indeed, a storage provider may be honest, it will behave correctly, but curious, it may try to look at our data. Moreover, a dishonest provider may try to misuse or exploit the user's data. For instance, we saw at the beginning of this year the Facebook and Cambridge Analytica data scandal. It exposed more than 80 million of users' data. So this fear is not without a reason. Moreover, a user may fear that his data is somewhere in the world in a not really secure place. And once he wants to control the data location, he needs to pay more. He needs a special service level agreement. In addition to that, we witness new powerful attackers. On average, every 2 months, we witness a data breach, a large data breach. Like last year, we had this Equifax scandal. 143 million victims had their financial data, like credit card information, exposed. This year, in May, it was the Singapore health insurance company that was attacked with more than 1 million victims only in the city of Singapore. Some of the attackers are even able to acquire encryption keys using like bribery or coercion. So what we can do if we want to keep our data in the cloud, but at the same time we want them to be protected. The straightforward solution, of course, is to encrypt data before the outsourcing. It is the solution recommended by the recently introduced European General Data Protection Regulation that states that not the data owner, but the cloud, the data owner and not the cloud service should hold the encryption keys. So it's the data owner that is responsible for the protection of the data. This is, of course, a good solution. But imagine if now we encrypt data using like AES with a 128 bits long key or 256, but maybe after a decade this protection will be not enough. So in the long-term storage context, this protection may not be enough. Moreover, as we saw now, some attackers are even able to acquire encryption keys. And against such an attacker, this solution will not work. So all this introduction leads to the following question. How to protect encrypted data against an attacker possessing the encryption key? Is it possible? Yes. We will follow the 3 steps to do this. First, in the first step, we will transform the data using an all-or-nothing method. This method will produce a ciphertext that is only possible to decrypt only if it's gathered in totality. So a partial decryption of the ciphertext is not possible. Then, in the second step, we will fragment such ciphertext into K fragments. All of such fragments will be needed for the data reconstruction, as the totality of the ciphertext is not in one of the fragments. And in the last step, once we transformed our data, we fragmented it, we will disperse them over K storage servers or sites. So an attacker will not only have to compromise all of the servers, but to acquire all of the green ciphertext blocks, but also to have the encryption key. Now we'll present some of the relevant all or nothing methods that can be used during the first transformation step. In fact, all or nothing is nothing new. It was introduced by Rivest in the 1997. The Rivest processing is composed of two steps. First, we have this all or nothing transform, which is a pre-processing step, during which we will take some plain text and encrypt it into a ciphertext using a key here denoted as KAONT. In the next step, this encryption key KONT will be XORed with the hash of the encrypted data and appended as the last block of the ciphertext. This way, if we do not possess the whole ciphertext, we are not able to obtain the data hash. And if we are not able to obtain the data hash, we are also not able to recover the KONT. So this is the AONT pre-processing step, and in the second step, such pre-processed data are encrypted again, using a different key. This time this key is denoted as K. So the reverse method protects against the exposure of the key K. Even if this key is revealed, still the totality of the ciphertext, the one that was obtained during the AONT transform, is needed. So 3 years after Rivest, Desai proposed some modification to the Rivest scheme that replaced the hash by a XOR of all the blocks. It allows to speed up the processing, but at the end it's a bit the same. So if we miss one ciphertext block, we are not able to obtain the KONT key. So both scheme, Rivest and Desai, they are able to resist an attacker that is possessing C-1 ciphertext blocks. The C denotes the number of blocks in the ciphertext. So we see an attacker, the red attacker, he has a key and he compromised all the servers, but not the green block. And still the data is protected. It is not possible to decrypt the data without this one missing green block. So those two methods, they work. The problem is that they require 2 runs of data encryption. And for a single user, this may be a problem. The processing starts to be slow. So it's why, like, after almost 20 years, the all or nothing methods were revisited by Karame et al. That proposed their own scheme, the Bastion. The Bastion paper introduces a new security property, the C-lambda blocks ciphertext access under key exposure property, that the acronym is CAKE. So we say that the scheme is C-lambda blocks CAKE resistant if it can resist an attacker that has all the ciphertext but lambda blocks of it. So, for instance, Rivest and Desai, they are C-1 blocks CAKE. We need all but one block of the ciphertext. The Bastion scheme relaxes a bit this property. It resists an attacker that can have C-2 blocks. So we need to protect at least two blocks of the ciphertext. But at the same time, it speeds up the processing, so it requires only one round of encryption. So how does it work? First, the plain text is encrypted into a ciphertext using a block cipher. Here it's CTR encryption mode. We could use also a different encryption mode. And then a transform is applied to the ciphertext. during this transfer, each ciphertext block will be XORed with all other ciphertext blocks. So like that, we create dependencies between ciphertext blocks. So when we think about a naive implementation of the scheme, it's obvious that it will be quadratic in complexity and maybe not so good. But if we implement it in a smart way, it will take just, it will be linear and take just two passes of XORs. In the first pass, we will calculate the XOR of the all ciphertext blocks. And then in the second pass, we will XOR each of the ciphertext block with the sum that we obtained during the first step. So at the end, we need 2C XORs performed in addition to data encryption. So this is much faster than encrypting data twice. Okay, now I will pass to the part of work that we did. So we started with revisiting the attacker model and adapting it to a more real use case scenario. In fact, what we observe is that if an attacker is able to compromise a storage server, probably he will be also able to get all the ciphertext blocks that are stored inside this single server. It's why we introduced the new property, the K-1 fragments, and not block cake property. So instead of expressing the security in blocks, we will express it in to fragments. So K is the maximum number of fragments, and we want to protect the data against an attacker that has all but one fragment. Why we want to do it? Because like that we can go even faster than the Bastion proposal. So I will quickly present the Ncpa game for the new cake property. We will say that a scheme is K-1 cake secure if the attacker is not able to win the game that is presented on the slide. Now I will explain the game. We have an adversary and a challenger. The adversary has access to a block cipher, to the inverse function of the block cipher, and the encryption key. The fact that he has the encryption key is different than the state of the art. Usually we don't give the encryption key to the attacker, but here we allow him to have the encryption key. Then the challenger has the same things, and moreover to that, he is able to generate a C0 initialization vector that will be used during data encryption. So the game starts, and the adversary will send to the challenger two plaintext, the plaintext 0 and the plaintext 1. The challenger will encrypt them and transform them using like the CON scheme, the fragmentation scheme. CON is the one that we will discuss later. And then the adversary will choose K-1 indexes that are corresponding to the fragments that he wants to receive. And the challenger will give him the K-1 fragments, but only of one, the one corresponding or to plaintext 0 or to plaintext 1. He will not tell him to which plaintext it corresponds. And then the goal of the attacker is to guess what fragments he received. If it is the fragments from belonging to plaintext 0 or fragments belonging to the plaintext 1. He decides, he may encrypt, decrypt, he can do whatever he wants using this block cipher and the key. And once he decides, he sends the A' to the challenger. If A' is his decision, is it the 0 or a 1? So the adversary wins the game if he was able to distinguish with a non-negligible probability the origin of the fragments. So later, when we will say that we are proving that our scheme is secure, we will say that we will apply this game. So once we relax the security property, we introduce our circular or nothing transform, the CION. It's the scheme that is k-1 fragment secure and is able to go faster than the Bastion's proposal. So how does it work? Similarly than in Bastion, we will take a plain text and encrypt it into a ciphertext. And then we will create sort of a chaining between the blocks. Each of the blocks will be XORed with its predecessor. Like that, we are not able to decrypt a block without its predecessor, so we have a sort of chain. Obviously, the first block does not possess a natural predecessor, so we will not XOR it. We'll do a special processing. We'll XOR it with k-1 special blocks that we will choose in a way that the indices are with gasps at least one between them, and that during dispersal, the transformed C0 block and the special blocks will end up in different fragments. So the pseudocode is presented on the bottom of the slide, but I will maybe just go directly to the example. We have a ciphertext composed of 6 blocks. We apply the CION transform to it. So we see that each block is XORed with its predecessor. So C1 is XORed with C0, C2 is XORed with C1, and so on. And the first block is XORed with one special block. We'll choose one special block because we disperse over 2 sites, 2 fragments. So we need k-1 special blocks. So in total, we need 1 special block. So the C0 here will be XORed with the special block that will be the transform block C3 prime. Later, we disperse our blocks to storage site 1 and storage site 2. And like that, we see that unless we gather all of the blocks, we are not able to obtain, like if we are just in the storage site 1, we are not able to obtain a single ciphertext block. So we are also not able to decrypt it. Our comparison with relevant works. So we see a table comparing the number of operations and the security of the presented schemes. We have CION that is at the bottom. We see that similarly to Bastion and to just encryption, it requires 1 round of encryption. Then, in contrast to Bastion, it applies less XORs. It applies twice less XORs than Bastion. Why twice? Here we see this is the total number of XORs, including encryption. And in the brackets, we see the XORs that are coming just from the transform. So for Bastion, it's 2C. For us, it is just C. The K is usually a very small number. So if we compare it with the number of blocks in the ciphertext C, it's negligible. For the security, we see, of course, okay, encryption is not secure in the cake definition. The reverse and the SI, they resist an attacker unless that has C-1 blocks. Bastion resists an attacker that has C-2 blocks. And CION resists an attacker that has all but 1 fragment. So we are relaxing the security, but we are going faster. And this faster is presented in this benchmark. We implemented the schemes using the same technique, using Java, the same programming methods. The yellow is the baseline, the AES encryption using CTR. And we see that CION has a 7% performance overhead. And this is could be even reduced if we apply a more, like if we do a more fine-grained implementation of the scheme. And what confirms our complexity evaluation, the bastion is like around twice slower, like has twice larger overhead than a CON. Because of course we cannot reduce the encryption time. And then revest and decide are slow, much slower than the two bastion and CON schemes. So I will pass to the security analysis of the CON, and I will start with explaining why we can use the same security analysis than the bastion scheme. Because in fact the two schemes are very similar. We start with the remark about the bastion, that if we take two blocks, ciphertext blocks from the bastion schemes, Ci prime and Cg prime, we XOR them together, we will obtain the Ci XOR Cg. So we see, using this remark, we take a fragment from bastion and we transform it like that instead of having blocks XORed with a sum of everything, we have the majority of the fragment will be consisting of just XORs of two elements. So the one scheme can be reduced to be very similar to what we have. The difference will be here. The first C0 in bastion, that is also the initialization vector. In bastion, it's XORed with all other ciphertext blocks. In our scheme, it is XORed just with k special blocks that are in different fragments. So here we gain the performance by changing this C0 reconstruction. We go to the security analysis. We have the basic, the most important lemma. We have that given any k minus fragment, so we want the k minus 1 cake property as output of the CON. It is infeasible to compute any ciphertext block. And why it's like we show that if we miss one fragment, we also miss one special block. This special block is an output of the CTR encryption mode, and so therefore it is pseudo-random. It can take any of 2 power the block size possibilities. And so we are not able to reconstruct any of the blocks without the missing fragment. But the problem is in bold. Like we follow the bastion proof, and then we saw that are we able to say that the output of the CTR encryption mode is really pseudo-random? Usually it is, but in this special situation, the attacker has the key. And if I cite the introduction to modern cryptography, it is meaningless to say that a block cipher is pseudo-random if the key is known. Indeed, if we repeat the Ncpa game with an adversary, instead for just CTR mode, an attacker gives to the challenger 2 plaintext blocks. He will receive 1 ciphertext block and has to guess to which plaintext this block belongs. So we see that if this is the result of encryption using the CTR mode. So we see that if an adversary knows the plaintext, and this is the case, but also knows the encryption key, so can invert the BC function, he will be able to obtain the C0, the initialization vector, and win the game. He will be able to distinguish between two encryptions of plaintext. So we have a problem, but On one hand, the output of CTR is not pseudo-random, but here we are using linear combinations of this CTR output. So the thing, and they are maybe pseudo-random. So we formulate sufficient but not standard hypothesis for cake security, that any C XORs sum of 2 or 3 terms of the block cipher, BC block cipher applied to C0 XORed some I, the counter, are indistinguishable from C random values. So if this proposition is true, then the security proof for CION and also for Bastion works. But this hypothesis is not standard. We cannot really, we did not prove it yet, and we cannot find it in the literature. So why, instead of basing on this hypothesis, what we suggest is to make the CION and also Bastion secure under more standard assumption. And here we propose 3 variants how to do little changes to be able to use standard security assumptions. And the first change, the first variant, will be to secret shared initialization vector C0. Because in both schemes, the CION and Bastion, this vector, this C0 is a special block. Once it's revealed, it allows the attacker to win the Ncpa game. And this is a solution a bit similar to the Kravchuk's secret sharing mesh short. In Kravchuk, it's the encryption key that is secret shared and attached to the fragment. Here, what we want to do is to secret share the C0 and attach the shares of C0 to the fragment. Usually, the cost of perfect secret sharing is quite high, but in this case, it will be negligible as this is just one block of data, just 16 bytes. And the second variant is, we saw that the problem with the pseudo-randomness lies in the fact that we are able to invert the block cipher function. But we can replace this block cipher function, and instead of using like AES, we could use like a one-way function. And then the problem of an attacker that is able to invert this function is solved. This is not usual, but not forbidden. And moreover, it can accelerate the performance. In fact, if we use a CTR with a one-way function, like a hash, it will go faster than just AES, especially as we can, hash is nicely parallelizable. We could use it, accelerate it using a GPU. And the last variant is, instead of using CTR, that is fast, but we have some problems with this mode of encryption, we could just use the Cipher blockchaining in addition to the secret shared initialization vector C0. In CBC, the entropy grows quite quickly, and we don't have the same problem than with the pseudo-randomness of the output. The disadvantage will be that it will slow down the computations, because as we cannot parallelize the processing, in CBC the processing is sequential. It's like a chain, so we will go for sure more slowly. Well, I'll pass to the conclusions and future work. We are now working on an extended security analysis of the scheme. And in the next step, we are planning to do a fine-grained implementation of the CION to reduce this 7% overhead that we have now to even more, to like 1-2% of performance overhead. And also, we would like to implement and evaluate the 3 variants, especially the variants with the one-way function instead of the block cipher, that is invertible, as it could accelerate the fragmentation processing. So thank you for your attention. No questions.
Can you describe a little bit the benchmark?
Yeah, sure. The performance benchmark?
Yeah.
Okay. Which?
I mean, from the performance control.
Okay, yeah, so we have the performance into megabytes per second.
Implemented in what?
In what? Yeah, it was in Java using the standard Java crypto library for AES. And then everything that's every component was already in the Java standard library. So we have the AES, the hash functions, and the XORs. Okay, there are the.
Parallel computing or just?
No, it was like here. It's none of the scheme is parallelized. So we are not gaining performance using tricks, programming tricks. It's just it's really the same. The difference, for instance, between CON and Bastion is that in Bastion we will have 2 for loops that are going through the data, and in CON we have 1. And the Bastion loops, they can not be really parallelized. So that's.
So there, when you say more fine-grained implementation?
Yes, because first it's Java and not C. So in C we could go faster. And second, here we have still we apply first the AES from the Java library, and then we apply a second round where we do the XORs. And this could be done like in one function, but just needs a bit more programming. That's okay.
Let's suppose that you have a document that is changing in short time. For example, you're writing a Word document, a very large one,
yeah.
And it has been fragmented, and you know that you're working on a specific fragment. You need to rework the whole thing, or there is a way that you can just change?
I'll just change a slight
part of it.
Like for sure, for the revest and the SI, we are not able because it's encrypted twice, and we are obliged to decrypt. In Bastion also, the blocks are depending on everything, so probably not. But maybe in our, as it's a chain, we would be able to modify. But still, that's a good track. Yeah.
When you say that the first one you encrypted with a special block, how do you obtain the special block?
The special, the special is just our definition. It's just with any block from a different fragment. So we just have to choose a block that will be in a different fragment, like not to have the special blocks in the same fragment. But apart of that, the special blocks are not special. Stack.
Just to understand, fragments are sets of blocks that sit in the
Yes.
Okay.
Yes.
Because your security, let's say, based on fragments and.
Yes, exactly. So if we see we have the scheme. So we have the blocks, and the fragment is the whole bunch of blocks that is stored. We assume that one fragment per server and not more.
And in your performance evaluation, what is the architecture of your simulation or performance evaluation? Because I'm looking to the slide, I don't understand.
It's just the performance, like it's the time of processing. For instance, we have it's on my device, so before sending the data, the fragmented data, I just need to wait some time to encrypt and process them. And the performance evaluation will tell me how fast it will go. So how long I will wait until the data can be ready to be outsourced.
The retrieval is not included. So
Yeah.
It's just the kind of processing and not the networking.
Yes, it's not. Yeah, we don't measure the latency time or the time of distributing. It's just this one component that's transforming the data.
So you evaluate these performances on your machine or on a specific server? How many cores?
On my machine, not this one, but a very similar one.
How many cores?
I have the specifications on the 4 cores, but I think we don't use parallelization. Nothing, just.
But doesn't Lava do it automatically? Because I know.
Yeah, we did some tests and no. So on the machine also CTR and CBC was working the same way.
Yes. So what happens? I understand that the idea is you send like fragments of your data to different providers.
Yes.
What happens if one of those providers isn't available? Can you decrypt all the remaining data?
It's a good question because so here we present, of course, the way of protection, but in a real use case also, in all these techniques are combined with some other techniques for resilience. So usually we will fragment data using into K fragments, for instance, like four or more. But then we will add redundant fragments using like Reed-Solomon codes. And of course, like that, we will have like 4 fragments out of 6 that are needed for the data reconstruction. It's a bit a compromise. Of course, then the attacker has more choice, but we are protected if we lose one of the fragments or 2 fragments.
The mapping between blocks and fragments known, or you have just contiguous sets of blocks?
Yeah, in Bastion, yes. Here, what we propose the dispersion. We could also to take just big bunch of blocks, but what we do is we do like consecutive blocks are going to different fragments, and why? Because okay, imagine a situation that. We don't know how, but the attacker will get the C1 like this, so he could deblock the whole chain until the end of the fragment. And with this method, the chaining will stop. That is, yeah. So this is like an additional measure because it costs nothing to distribute them like that instead of cutting in big chunks. No.
Thank you.
Okay. Thank you.